the relationship between speed and accuracy has always been, a little, a little bit of a battle, right? That engineers don't trust an answer if it comes too fast, right? Because we kind of know the real world is nonlinear. The real world is full of noise, and it's sometimes really hard, right? All models are wrong, some are useful, and that's because models are simplified versus the real world. And if you take a model and you simplify it so much that it becomes seconds to solve, engineers don't want to trust it. So how do we do that? Well, of course, as we mentioned, training data, and you want to feed it, say, dozens or even hundreds of prior sets of data. That can be a simulation, a trustworthy, full physics simulation, and that can be some test data, right? But what we do with that, and I'll give you an example of CFD, right? So I plug in, my geometry. I have, a couple million cells, and a couple million cells inside of that takes hours to converge, okay? So I've now waited and plugged in all this information, but I've got a reliable answer, and I know it's going to match test data. Takes me, hours, right? The reality is once you've converged that, and you've got a full field of temperatures, pressures, velocities, densities, whatever, the reality is if I did a sensitivity study on the inputs and understood how much they impacted the outputs, I could actually take this full field, millions of cells, and break it down to a very, very simple equation. I could reduce millions of degrees of freedom down into a pretty simple relationship. My in is this, and my out is that. And that's what we call a reduced order model. So I'm reducing the order of the problem. The order started off as millions of degrees of freedom. Now I'm reducing it to 5. Right? If that reduced order model is accurate, I can now predict the answer of millions of cells and thousands of iterations of CFD in a matter of seconds. Because I have a trustworthy relationship, a mathematical relationship between my inputs and my outputs. That's how it's working. That's how it's so fast. The million-dollar question, of course, is if the reduced order model is representative of the full physics. And again, that's with training it with a broad range, deep set of training data.